Hello. I figure everybody's pretty rusty after having several weeks off from linear algebra. So I wanted to give you a few small videos reminding you of a few things you were supposed to have understood how to do before the break started. So for example, let's say you're trying to prove a set of vectors forms a linearly independent set, right? So if you're trying to prove some set of vectors, v1, v2 through vp, forms a linearly independent set. It's independent set. Well, remember what that means, what the definition of linear independence was, right? And that's how a lot of these things are solved. You just have to have that definition on tap so you can use it. So to prove that, that's equivalent to saying that forms a linearly independent set if any time you form a linear combination of those vectors, going from 1 to p, and set it equal to the 0 vector. If you assume that, and what happens is that all the ci are equal to 0 for all I equaling 1 through p. Okay, that's equivalent to saying that they are linearly independent, right? That any linear combination equals a 0 vector forces all the coefficients to be equal to 0 scalars, right? Let's look at an example of how we do this. First example. So let's say we're trying to figure out question. Let's say the question is this set of vectors with good old 1, 2, 3, 4, 5, 6, 7, 8, 9 as column vectors in it. Is this a linearly independent set? Okay. Let's say that's your question. All right. If I call this first one v1, this one v2, and this one v3, there's column vectors, if I give them those designations, then when I'm going to answer this, I just remind myself of the definition, right? These vi are linearly independent if and only if any linear combination of them set equal to the 0 vector forces all the ci to be equal to 0. Okay, so you just remind yourself of the definition, you state that, especially when you're showing your work on a test or quiz, right? So you showed you know the definition, now apply it. Well, what does this look like? This statement here, let's write it out a little bit. That statement is equivalent, expanding the summation notation, C1 V1 plus C2 V2 plus C3 V3 is equal to the 0 vector. What does it look like in this example? It looks like C1, times the column vector 1, 2, 3, plus C2 times the column vector 4, 5, 6, plus C3 times the column vector 7, 8, 9 is equal to 0, 0, 0. So you write it out a little bit and then you go, oh, that's right, this is the same thing. So that's a vector equation, right? And that's always can be rewritten as a matrix equation. Matrix equation here would look like, you should be able to answer this. You might want to stop the video, try it yourself. Okay, let's see you come back. That's equivalent to saying this matrix multiplied by C1, C2, C3 is equal to 0, 0, 0, right? And that's equivalent to the augmented matrix. I'm gonna make sure you guys can see this. Yeah, the augmented matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. With the bar there, 0. That's equivalent to saying this has a solution. So they're linearly independent if this linear combination forces all the CI to be equal to 0. That would be equivalent to saying this vector equation forces all the CI to be equal to 0, right? And so on and so forth. So what we're looking to see is, after we use our REF on this, right? After we put this in row reduced echelon form, what it says about the CI. I'm just emphasizing that because a lot of students, after a couple weeks, they forget how to get out of the output to Gaussian elimination and get back into the system. So write things out a little bit, know your definitions. That's the way to do it. Okay, so if we do our REF on this, we end up getting this. Right. So 1, 0, minus 1, 0, 1, 2, 0, 0, 0, and of course, still a bunch of zeros over here. Okay, now you should stop the video and ask yourself, what does that mean? Can you interpret this back into this problem and answer that question? Okay. Make sure you can do it. Okay, if you did that, well, hopefully in the process of doing that, you realized that you can just unwrap this, you know? We got it into an augmented matrix by going from a vector equation to a matrix equation. Well, we can work it backwards. So this, bring this up here so I can work on it. And let's move you over so you can see that. All right. So that is equivalent to saying that augmented matrix is the same thing as matrix equation. 1, 0, minus 1, 0, 1, 2, 0, 0, 0, multiplied by C1, C2, C3 is equal to 0, 0, 0. So you just write out the matrix equation and then multiply that out. What do you get? You get C1 minus C3 has to be equal to 0. So now we're going from a matrix equation to a system of equations. C2 plus 2 times C3 is equal to 0, right? Multiplying that by that. And wonderful, 0. Now remember, notice what this says. 0 times C1 plus 0 times C2 plus 0 times C3 is equal to 0. That's not saying that all these Ci are equal to 0, which I've seen students do. In other words, this is the same thing as the system of equations. C1 is always equal to whatever C3 was. C2 is always equal to negative 2 times C3. And big news, 0 is equal to 0. So we have a consistent system. And in fact, we have infinitely many solutions because notice there's nothing specific about C3. So C3 can be any real number. So there's infinitely many solutions. Okay, well, we'll try one. So let's see. So suppose C3 is equal to 1. What does this say? Then C1 will be equal to 1, and C2 will be equal to minus 2. Okay, what does that have to do with our question about whether that's a linearly independent set? We said it's linearly independent if when you put it into a linear combination with these CI, and you get 0, that's going to force all the CI equal to 0. Well, that's not happening over here, right? This statement, this implies that, so I'm looking over here and replacing the C1, C2, C3 with an example of a solution that we came up with. This solution implies that 1 times 1, 2, 3 minus a 2, so minus a 2 times the second vector, 4, 5, 6, plus 1 of these third vectors, 7, 8, 9, will give you the 0 vector. Verify for yourself that's true, right? 1 minus 8 plus 7, that's 0. 2 minus 10 plus 8, that's 0. 3 minus 12 plus 9, you can add up to 0. So what does that tell you about these vectors? 1, 2, 3, 4, 5, 6, 7, 8, 9 are not linearly independent. And therefore, that's equivalent to saying they are dependent. Just remind yourself what that definition of dependent is. Can you see all that? Yes. Okay, so that's an example. Another example. A little bit faster this time. Let's change this set to be 1, 2, 3, 4, 5, 6, 1, 1, 1. I'll change things by writing this one in a different color. So this is our example 2. Here I've got 1, 1, 1 in here instead. Right? Does that change things? Maybe that's a linearly independent set. Okay, sorry. Let me get you back over here. Yeah, maybe that's a linearly independent set. So example 2 here. You can see that, right? Right. Okay. So again, they're linearly independent. If a linear combination of them adds force set equal to 0, forces all the CI equal to 0. So this gets changed to the 1, 1, 1. That gets changed to the 1, 1, 1. Ditto here. And now when we do our REF, what do we get in the second example? This time we get something that looks like this. No surprise that the first 2 columns stay the same, right? Because of all those equivalent row operations. Wouldn't really change the result in the first 2 columns. Last 2 columns look like negative 1/3, 1/3, and everything else is the equivalent. All right, so again, stop video, ask yourself what that means. What would you say? And come back. Should have that is equivalent to just this, right? What does that mean? Interpret that. Well, 1 times C1 minus 1/3 times C3 minus 1/3 times C3 is equal to 0. 1 C2 plus 1/3 C2. Sorry, let's see. C2 plus 1/3 times C3. There we go. It's equal to 0. And again, 0 is equal to 0. So now we just have this and this here. Right, that minus came along along with that 1/3 there. So that becomes a positive 1/3 here when you add it to the other side. So let's see. So again, C3 is free. C3 is free to be any real number. What would be a good choice? Well, for dividing everything by 3, why not choose C3 to be equal to 3? Then C1, which is 1/3 of 3, will be a 1. I'll rewrite it in red. And C2, if C3 is equal to 3, 3 times negative 1/3 gives you, gives you a negative 1. So that statement over there becomes, for 1, 1, 1 in here, what happens? We've got C1 is equal to 1, C2 is equal to negative 1, C3 is equal to a 3, and we have 1 minus 4 plus 3 equal to 0, 2 minus 5 plus 3 is equal to 0, etc. So there's a linear combination adding up to 0 where all these coefficients are not equal to 0. So once again, these are not linearly independent, they are dependent.